Hi guys, today's concept electromagnetic induction. So far we studied electricity and magnetism separately, but first time the combined effect of electricity and magnetism we will see in this chapter. So let's define what we know. So we know that electric current produces magnetic field that we learned. On the other side, a change in magnetic fields can also be used to produce electric current. So this is the first guess by the Michael Faraday. So we got a new concept, electromagnetic induction. So the definition of the concept says it is the process of generating a current through a circuit due to the relative motion between a wire and a magnetic field. When the wire is moved through the magnetic field or the magnetic field moves past the wire. So here I would like to highlight some words. Those are very important. So our ultimate goal is to generate current. Current should be generated without any source. We know that a cell is a source of EMF. It is the source of EMF. So here we don't use any cell, but we need to generate current or EMF. So for that, there should be relative motion. So this word is very important. There should be relative motion between a wire, two simple things, and a magnetic field. So to generate current, just we need a wire and a magnetic field. That's it. And between these two, there should be relative motion, not like stationary. And this motion may be wire moved through the magnetic field or magnetic field moves past the wire, or magnetic field can change. So this is a very useful, easy technique to generate current. So let us see that first. So very important that is that suppose if you have a magnet, you know that magnet is a source of magnetic field, and here a loop is connected to a galvanometer. And as per the convention, so the magnetic field lines are coming out from the screen. So these are the head of an arrow. So it means they are coming out. So this is the direction of magnetic field. So as per electromagnetic induction definition, so magnetic field is there and current loop is there. But here if you notice, the galvanometer shows deflection 0. So here the notice thing is no motion or no relative motion. If there is no relative motion, when there is no relative motion between magnet and the loop, the number of field lines which is passing through the loop constant, so that do not contribute any current. So there should be relative motion between the magnetic field and the loop what we selected. So here I am having a setup. So this setup, a coil, a loop which is connected to a bulb, and here voltmeter is also having evidence that how much voltage or how much EMF will produce. Now this magnet is at stationary, it is at rest, and since it is rest, it is also having its own magnetic field. So these are the magnetic field lines. So magnet is there and the coil is there. but there is no motion. Since it is at rest, no motion. So this causes no current in the circuit. So that's why the bulb is not glowing in the circuit. But when you make a move, so if you can move magnet with respect to coil, you observe there is a current in the circuit. The voltmeter is also deflecting. So this motion is necessary. So now if there is motion, there is current in the circuit. There is relative motion. This word is better. If there is a relative motion with respect to coil to the magnet, then that gives current in the circuits. So this is the concept of electromagnetic induction. So when you move a magnet, a moving magnet, what the moving magnet causes? So if the magnet moves with respect to coil, so there is a change in flux, change in magnetic field lines. So this is also nothing but we call that flux. So that flux causes current in the circuit. Now when the loop increases the number of field lines now passing through the loop, because the magnet is close to the coil, now that induces a current in the coil. Now that evidence we got it from the galvanometer. Likely if you can move away magnet with respect to coil, so this time also there is a change in flux. That change in flux now causes current, but this time the direction of current changes. So here you can notice that very clearly. So when there is a change in the magnetic flux, then there is a change in the direction of current. Now this is a very important point we need to observe. In the second case, if you moving the magnet away from the loop, then the number of field lines in this case decreases. If the number of field lines decreases, then there is an induced current in the circuit. So this word is very, very important, induced current in the circuit. And now this induced current is opposite in direction. So that's why the galvanometer shows deflection in the other side. Now, instead of moving bar magnet, suppose if you move a coil. Yeah, here you can see, here I have taken a stationary magnetic field or uniform magnetic field. Uniform magnetic field. So here I have set up a coil which is connected to a galvanometer, and now if I can able to move this coil. Yeah, now in this case also induced current will be set up in the coil, because there is a relative motion or change in flux that causes current in the circuit. So the magnitude of the induced current depends upon the speed of the relative motion. If the speed is more, then the induced current in the circuit is more. But one exception case is there. Be careful about this one. When the loop is moved parallel to the uniform magnetic field. Now if you can observe this loop having area, so this area vector, now the area vector is parallel to the magnetic field, then there is no change in the magnetic field lines that are passing through the loop, then no induced current. So this is a special case, or I can discuss this when I can go ahead. We can talk about magnetic flux and all. That's, we already know that. So this is some special case. So here I want to highlight a point that if there is a relative motion, the speed is more, then the induced current is more. So how fast you move the magnet with respect to coil, so that causes more current in the circuit, because if the relative motion is more, the number of magnetic field lines which are passing through the coil will be more, so that induces more current. Now if you notice that why the bulb is on and off and on and off, or if you notice very carefully at the voltmeter, direction of current in the circuit. So when I move inward, the voltmeter showing the positive direction. When I move outward, the voltmeter showing the negative direction. So why the voltmeter is showing here both positive and the negative direction? Because when we move inside, the current will be the flow in one direction in the circuit. When we move outside the bar magnet, then the current will be flow another direction. So in the both the cases, there is a change in the magnetic flux lines with respect to coil. So that causes induced current, but here the induced current direction, my dears, this word is very important. Induced current direction will change. The induced current direction will change when you move in and out. We know that a current carrying coil is also a source of magnetic field. Other than the bar magnet, so we are having another magnetic field source, a current carrying coil, also a source of magnetic field. Now in this case, if you use that current carrying coil as a source, so this is a source. So in this diagram, you are seeing the two coils. So one coil is connected to a cell via switch, and through this coil, current is flowing. So now this will be source of magnetic field. A current carrying coil is a source of magnetic field. Now if we bring close to another coil, so here you can see there is another coil. So this coil is not connected to any source. There is no battery, there is no connection, nothing. Only it is connected to a galvanometer. Now this coil is close to this source coil. So the source coil produces magnetic field direction. So this is the direction of magnetic field. Now when you on switch, current will be flow. When current flows, then there will be magnetic field, a momentary magnetic field. Because here it is a DC source, there will be momentary magnetic field. So in that case, so the galvanometer which is connected in another coil will shows the deflection. So here there is induced current in the second coil due to current flowing in the first coil. This is something is very interesting. So that induced current in the second coil is due to because of the magnetic field which is producing in the first coil. So this thing happens when you just on switch. maybe typically a few milliseconds. So same thing happens when you switch off. So when you switch on, initially there is no magnetic field. I can take that as zero magnetic field. Then soon after you on switch in the first coil, the current flows, means current to maximums. Current will be maximums. So the magnetic field is also initially zero. When the current flows, then the magnetic field will becomes maximum. So here it is a change. Initially it is zero. Then when current flows, then magnetic field generates. It means it becomes maximum. So there is a change from zero to maximum. So that change of the magnetic field in the primary coil causes induced current in the secondary coil. That's why the galvanometer shows deflection in one direction. Now when you off switch, now this time what happens? The current initially at maximum, so it means magnetic field is also existing. It's also, let me take as maximum. When you off switch, then current goes to zero. Then by the time magnetic field will become zero. Now here also there is a change in the magnetic field. So the magnetic field is changing from maximum to zero in the first coil. Now that causes induced current in the second coil. Now this time you can clearly observe the direction of induced current in the second coil changes. Now that is a very big change. When you on in the first coil, the direction of induced current in the second coil is one direction. When you off switch in the second case, so in the first coil if you off switch, there is induced current, but the direction of induced current in this time will be opposite. So this is also something very interesting. So here I am having a stimulation help. Now it is a setup of two coils. Suppose if I take this is coil 1, so this is second coil, coil 2, and the first coil is connected to a source. So this is a battery having source, and the second coil just connected to a bulb at here. Or for a moment if we can connect it to a voltmeter, so we can understand the direction also very clearly. Now in the first coil current is flowing, so here you are seeing a tiny dots, they are electrons. Electrons are flowing in the first coil, and here in the second coil if you can see, there is no deflection in the voltmeter. So to get the deflection in the voltmeter, what I need motion, or particularly it is a relative motion. Suppose if we can move the first coil with respect to second coil, so there is change in the magnetic field of the first coil with respect to second coil. So that change causes induced current in the second coil. Now that induced current shows in the voltmeter. So we can see that with the help of bulb. So when you can move fast, so then if you can see the current which is flowing in the second coil. So this causes relative motion, causes induced current. So that's why the bulb is on and off, on and off. So, and not only that, you can clearly observe the motion of electrons, tiny dots in this second coil. So, when I move the first coil with respect to second coil in and out, so the electrons direction also changes. So that's why the bulb is not glowing continuously, it is glowing on and off. So if I make move off like this fast, so then it will be just like on and off. Or here I am having another option, so I can flip the switch. So instead of the moving the first coil with respect to second coil, suppose if I play with the switch at here, so let me take close to the second coil. If I can play with the switch on off, so when I can on, so that will be the direction of current in one side, and when I can off, that will be the direction of current in the another side. So this action we cannot observe because it is barely taking milliseconds. So if you can play like this by flipping the cell or source with respect to first coil, so that causes a change in the induced current. The change in the magnetic field. So that change in the magnetic field causes induced current in the second coil. So with the help of the magnetic source, a bar magnet, so magnetic source also we can produce induced current. So finally we can conclude that the current induced in a loop is caused by an induced electromotive force or EMF. That EMF is due to electromagnetic induction. And we know that in any circuit, suppose if I am having a circuit, it's a bulb. So this bulb, to glow the bulb, we need a source. So here I have taken source as a cell. A cell is a source of energy, chemical energy converts, and the cell causes motion of electrons in the circuit. So this is, if this is current direction, electrons direction is opposite direction. So the electrons move due to because of a force. That force we call as EMF. But when it comes to electromagnetic induction, there is no cell. So we were finding an alternative source of a cell, that is nothing but change in magnetic flux. Now that change in magnetic flux induces current. An EMF represents energy capable of moving charges around a circuit. We studied this about in the batteries as a chemical source of EMF. Now from this concept, we learned that a moving magnet can create an induced EMF in a stationary loop which causes current, and in the case of two stationary loops, when the change in current in first circuit induces an EMF in the other, and this is known as mutual induction. So these are experiments performed by Michael Faraday, Joseph Henry. So they both are conducted independent experiments regarding the electromagnetic induction around 18th century. Finally, Faraday drew the conclusion that an induced EMF is produced in a loop by changing the number of field lines passing through the plane of the loop. Again I repeat, this is the Faraday's conclusion. An induced EMF is produced in a loop by change in the number of field lines So this words is very important. Change in the number of magnetic field lines passing through the loop. So this is a very easy technique. Just to produce current, we need a conducting loop and a magnet. Just to play the magnet with respect to current loop, so that induces current. Such a great work did by these two fellows, Michael Faraday and Joseph Henry. So let me recall about what we already know, because we're discussing about a change in magnetic field. So I would like to draw your attention towards that magnetic flux. So magnetic flux is a measure of a number, or we can define that the number of magnetic field lines which is passing through area, that we define as magnetic flux. We represent that with the phi. So flux phi equal to, if you remember the formula, phi equal to B dot A, the dot product of two vectors, area vector and magnetic field vector. Flux phi equal to BA cos theta. Here theta is the angle between the magnetic field vector and area vector. Here area vector is nothing but area of the loop, area of the conducting loop. So that's fair enough. So if you place a conducting loop in a magnetic field, the conducting loop itself having area, and if you are rotating the conducting loop with respect to magnetic field, or if you can change the magnetic field with respect to conducting loop, both of the way it can be possible. So then that causes a change in the magnetic flux. Suppose area can be represented a vector capital A, which is perpendicular to the plane of the area. Yeah, area is always perpendicular to the plane. Suppose if you can take, my palm is a rectangular conducting area, just insert a vector or a perpendicular vector. So this will represent the direction of area vector of the loop. So as per from the formula, if you can take flux pi equal to, so I will write a side. So flux pi equal to BA cos theta. Now if theta is the angle between area vector and the magnetic field vector, if theta equal to 0 degree, so cos 0 contributes to 1, then the flux phi value will becomes maximum. Suppose when the theta equal to 180 degree, so from this below figure if you can see, so this is the theta angle between the magnetic field. So the magnetic field, I will draw the black arrow, so this is the direction of magnetic field, and the area vector I will draw the pink arrow. So they both are in the same direction, parallel, the angle equal to 0. So in the first case. But when it comes to second case, area vector and magnetic field vector, they both are in the opposite direction. Therefore, angle between them goes to 180 degree. The flux pi equal to negative BA minus BA. So in the both of the cases, flux value is maximum minus. But minus tells about that the area is opposite in the direction of the magnetic field. That's it. But flux is a number. Keep it in mind. Flux is a number. We want that only. And when theta equal to 90 degree, when theta equal to 90 degree, cos 90 contributes value 0, but the flux in this case goes to 0. We cannot get any flux. But when theta equal to at any angle, when theta equal to angle A between the magnetic field vector and area vector, then we need to find out that. So by using the formula flux pi equal to B dot A, we will figure it out what is the amount of the flux which is the enclosing by the magnetic field. So this is the background knowledge we already have. So finally, I can give a formula for magnetic flux phi equal to BA cos theta. Here B is magnetic field and A is the area of the loop and theta is the angle between B and A. And the units of magnetic flux Weber, and 1 Weber equal to 1 Tesla meter square. And to increase the flux, suppose we need such a cases, so in that case the flux number of magnetic field lines should be more. So by seeing the formula we can understand that, so the flux is depend upon the theta of the magnetic field and area. Not only that, the flux will be increases or decreases by changing area of the loop or the changing the strength of the magnetic field also. Not only that, if you can add more number of loops, instead of taking one loop just like a one conducting loop, suppose if you make this conducting loop of n, so the loop is made up of n squares. So then we can change the formula that the flux pi equal to NBA cos theta. So in this case we know that a solenoid having n number of turns. If the turns increases, the strength of the magnetic field is also increases. So the magnetic flux is also depends on now number of turns and the strength of the magnetic field and the area of the loop. So finally, we can say the Faraday's laws in terms of a mathematical relation, that is the EMF E equal to the negative of the rate of change of magnetic flux in the circuit. Again I am repeating, the EMF, here EMF is nothing but induced EMF. The induced EMF equal to the negative of the rate of change of magnetic flux. Here phi suffix m is nothing but magnetic flux and delta T is nothing but rate of change. And if this rate of change is more, then induced EMF is also more. Or if the rate of change of flux is more, then the induced EMF is more. And here the minus sign, oh, this is very important. Here the minus sign tells about the direction of induced current in the circuit. Again I am repeating, here the negative sign tells about the direction of current in the circuit, direction of induced current in the circuit. Suppose if the coil having n number of turns, so in this formula we need to include the n also. So the formula will be changes as EMF equal to negative of n times d pi by dt. So this is all about Faraday's laws. So in the mathematical form of Faraday's laws. So in the next concept we will see about precisely about the negative sign that will give by the Lenz law.